Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we will look at approximating solutions to Laplace's equation in 2 and 3 dimensions. So in this topic we will once again revisit Laplace's equation. We will discuss solutions to Laplace's equation in 1 dimension. We will then convert the equation to a finite difference equation in 2 and 3 dimensions. We will then discuss how we can take this to create a system of linear equations that allow us to find an approximation to the solution to Laplace's equation. We will be looking at a number of examples in both 2 and 3 dimensions. In 2 dimensions, we will actually find the system of linear equations. In 3 dimensions, we will simply discuss how to get those linear equations and look at the approximation of the solution. Laplace's equation is reasonably straightforward. It simply says that the Laplacian of a real-valued function of a possibly vector variable is equal to 0 everywhere. This says essentially that at every single point of interest, the sum of the concavities is equal to 0. Now, you will recall that concavities are proportional to acceleration and force is proportional to acceleration. Consequently, this is essentially saying at every single point, all of the forces at each point are balanced. So, if all of the forces are balanced, there will be no change to any velocity within the system, and if the system is not moving, it will remain in a steady state. We'll be examining this last case. Now, in 1 dimension, Laplace's equation says that the second derivative with respect to the one variable is equal to 0. Well, that essentially says at best u of x can be a straight line, and that's about it. So u of x must be of the form ax plus b. Now, a solution to Laplace's equation in 1 dimension must be decided by boundary values. So, for example, if we have 2 Dirichlet or fixed boundary values, then there is a trivial unique solution. It is the straight line that passes through those points. If the left-hand endpoint has a Dirichlet boundary condition while the right-hand endpoint has a Neumann boundary condition, then the solution again is trivial. The Neumann boundary condition gives the slope, while the Dirichlet condition gives you the value at x equals a. And you can figure out what the result is if the conditions are swapped. Now, interestingly enough, if there are 2 Neumann conditions, then we either have no solutions if the slopes are different, or infinitely many solutions if the slopes are the same. So hopefully that should ring a bell from, say, linear algebra. So there's either a unique solution in the first cases, or in the last case, there's either 0 solutions or infinitely many solutions. So that should sound familiar at this point. Notice that if we have a solution to Laplace's equation, then it is also a steady state solution for both the heat equation and the wave equation. For after all, if the Laplacian of the function is 0, then according to both of the 2 previous equations, with the heat equations, the rate of change is 0, so there's no change to the system, and for the wave equation, the acceleration is 0. Consequently, any approximation of a system that obeys the heat equation must ultimately converge to a solution of Laplace's equation. A solution to the wave equation, on the other hand, ends up oscillating around a solution to Laplace's equation. Also, if the initial state is already a solution to Laplace's equation for either the heat equation or the wave equation, then there will never be any motion in either, and that will be the steady state for all time. Now, in 2 and 3 dimensions, Laplace's equation becomes a little bit more interesting. Now, rather than writing this as a vector-valued function, because we're restricting ourselves to more or less just 1, 2, or 3 dimensions, I will be using x and y and then x, y, and z. So now it's just that the sum of the 2 second partials is equal to 0 for 2 dimensions, or it's the sum of all 3 second partials all summed together equaling 0. Now, in 1 dimension, to get an appropriate unique solution, we needed boundary conditions at both endpoints. So we needed an interval of the real line, and we needed information at the boundaries. Well, in 2 dimensions, if we want to see or find a solution to Laplace's equation, we have to find the solution on a region in the plane. And this region must have a specific or specified boundary. In 3 dimensions, this requires a volume in R3, and once again, this volume must have a specified boundary going around it. The other point about this boundary is that either a Dirichlet or a Neumann condition must be specified at each point of the boundary. Now, the Neumann conditions we'll be looking at in this topic will be restricted to insulated boundary conditions. Let's look at some applications of Laplace's equation in 3 dimensions. These include, for example, suppose we had a room which is completely sealed, so there's a boundary everywhere, and every point of the wall is either insulated or at a fixed and possibly different temperature. For example, you may have a heater in one corner, or you may have a cooling unit in another. Well, the steady state that the temperature of the room will go to as you wait for it to stabilize ultimately will approach a solution to Laplace's equation. Interestingly enough, the gradient of the solution to Laplace's equation would of course also be the direction of maximum increase of temperature at any point in the room. Similarly, if every point on the boundary of a volume has either a specified fixed voltage or is insulated, and the region itself is devoid of any charges, then the potential throughout the region is specified by a solution to Laplace's equation. And once again, the gradient of the solution specifies the direction that a test charge would follow. As before, to approximate solutions to Laplace's equation, we will substitute our divided difference approximations for the second partials into Laplace's equation. So here we have those 2 substitutions. Consequently, if U is a solution to Laplace's equation, then this should be approximately true. Also, if we find a solution that satisfies this finite difference equation, then the solutions should be close to the actual solution to Laplace's equation. All right, let's simplify this. If we were to multiply both sides by negative h squared and, well, the right-hand side is 0, so it doesn't really matter, we get this expression here. 4 times u at x and y minus 4 different terms. All right, how are we going to approximate a solution to Laplace's equation? Well, here, for example, is one such possibility. Here we have a printed circuit board, a PCB, and there are some traces. And suppose that we know that at one particular time, the traces hold these voltages. Consequently, these voltages will cause effects outside their immediate vicinity, and we would be interested to see if there are any impacts or interferences as a result of this. Okay, so we notice that this PCB is contained within a rectangle from a sub x to b sub x in one direction and a sub y to b sub y in the other direction. We're always going to assume that the region we are attempting to approximate the solution to is a subset or contained within some rectangular region, now in R2, but also later in R3. In this case, the entire outside is assumed to be a boundary that is insulated. However, any of the traces shown in yellow also represent boundaries. So what we will do is we will divide this region into n sub x by n sub y squares, where each square is h by h in size. And then we will define the points x sub I being a sub x plus I times h, and y sub I being a sub y plus j times h. Consequently, x sub n sub x will be b sub x, and y sub n sub y will be b sub y. All right, so now we've divided the entire circuit into a grid. All right, so let's now substitute x sub I and y sub j into our finite difference approximation of Laplace's equation. You should get the hang of this by now. After all, now we have that x sub I plus h is just going to be equal to x sub I plus 1, and so on and so forth. So y sub j plus or minus h is equal to y sub j plus or minus 1. Okay, let's substitute all of those plus or minus h's with a reference to either the previous or the next value. Now, we don't know what the solution is at x sub I and y sub j, so instead what we will do is try to approximate it with an unknown, and we will try to calculate that unknown. So we will try to calculate u sub ij, and 4 times that value minus this sum of other values is equal to 0 according to our finite difference approximation of Laplace's equation. We can visualize this finite difference equation as follows. The relationship is between the value of the solution at a point and the value of the solution at 4 points around it, and that's it. So this essentially says 4 times the value at uij minus the sum of the values of the solution at the 4 points around it must equal 0. Now, note what this equation says. Rewrite it as follows by bringing all of the negated terms to the other side. Now divide by 4. So this says for this finite difference approximation of Laplace's equation, the central point is the average of 4 points around it. And that's really what Laplace's equation says. Every point is the average of the solution around it. So this is what we will use to find these approximate values. If u satisfies Laplace's equation, then u of xi and yj will be the average of the points around it. Now, going back to our PCB example, if a particular point is a boundary point, then its value is specified, or a property being insulated is known about it. So on this particular PCB, every single point in red is a boundary point and therefore has some sort of value. We are claiming that, for example, the lower trace is at 5 volts, the top middle trace is at 15 volts, and the three-pronged trace is at 0 volts. We also said that the border is going to be insulated. On the other hand, at every single point on this PCB that is white, we do not know what the potential is. Of course, we can sort of guess that, say, between the wire that's at 5 volts and the one that's at 0, then it's going to progressively drop. And perhaps between the 0 volt wire and the 15 volt wire, it will be 7.5 approximately. But we don't really know, so we have to approximate this solution everywhere. Let's zoom in. Let's look at the point u sub 2, 4. That's the approximation at x sub 2 and y sub 4. The finite difference equation says, therefore, that 4 times the value at this point minus the value at that point, minus that point, minus the value there, and minus the value there, those must all equal 0. Okay, that gives us a linear equation in 5 unknowns. Let's zoom in on this point, u93. And again, the finite difference equation says that u93 multiplied by 4 minus the value there, minus that value, minus that value, and minus that value is equal to 0. But notice that u92 falls on a trace that is known to be at 5 volts. Consequently, we can replace u sub 92 with 5 volts in the equation. And because that is now a constant, we can bring that to the other side. So now we have a linear equation in 4 unknowns. Now let's zoom in at the point 8, 6. All right, there we see the point there, and the finite difference equation says that 4 times the value at that point minus the value there, minus that value, minus that value, and minus that value is equal to 0. However, those last 2 points each falls on one of the 2 traces, and the first trace is at 15 volts while the second trace is at 0 volts. Consequently, we can replace the values of u87 and u85 with those boundary values. So that simplifies our equation, and we can bring the constants to the other side, giving us this linear equation in 2 unknowns. 3 unknowns, actually. Now let's zoom in at the point 8, 6. All right, there we see the point there, and the finite difference equation says that 4 times the value at that point minus the value there, minus that value, minus that value, and minus that value is equal to 0. However, those last 2 points each falls on one of the 2 traces, and the first trace is at 15 volts while the second trace is at 0 volts. Consequently, we can replace the values of U87 and U85 with those boundary values. So that simplifies our equation, and we can bring the constants to the other side, giving us this linear equation in 2 unknowns. 3 unknowns, actually. All right, I said previously that the outside boundary of this PCB is assumed to be insulated. Well, wait a second. If it's insulated, then how do we deal with it? How do we don't have something to substitute? Well, actually, we sort of do. Recall that an insulated boundary point means that the derivative of the solution at that point is equal to 0. And we're going to focus only right now on insulated boundaries. Well, if the derivative is 0, then the partial in that direction is equal to 0. And so if that expression is equal to 0, we can multiply both sides by h, which gives us that U89 minus U88 is equal to 0, or in other words, U89 is equal to U88. Okay, so we have the insulated boundary point at U89, and we will replace that value with U88. So we now have that value located there, which cancels out one of the 4 U88s. We also have the minus 15 at the other side. Okay, so that allows us to simplify this particular linear equation to 3 U88 minus U98 minus U78 equals 15, and that is now again a linear equation in 3 unknowns. Now, in the original PCB, there are 89 unknowns in this particular layout. Consequently, if we were to repeat the process we just saw at each of these 89 points, each of these 89 points would contribute one additional linear equation, and the only unknowns in each of those equations would be other points from those 89. Consequently, there would be a single solution. That's nice. So now we could solve the system of 89 linear equations and 89 unknowns, and that would give us our approximations of the potential at each of the unknown points in white. Here's an easier example. We have a room where most of the walls are insulated. However, there is a window facing outside where it's minus 5 degrees Celsius, an interior door which is at approximately 18 degrees Celsius, and a fireplace that is estimated to be 100 degrees Celsius. Of course, the fire is significantly warmer. However, most of the heat of a fireplace ends up going up the chimney. So we'll use 100 degrees Celsius as an estimate. Now, we do have one interior wall which is assumed to be insulated as well. Consequently, here is the grid into which we will divide this room into. Now, there are 11 interior points shown here, given this particular grid. Of course, if we had a more dense grid, there would be more points. But for this very simple grid, there are 11 points. I will simply give each point a label from 1 to 11, and we will write down the linear equations based on those labels. Now, looking at U1, 2 of the 4 points are insulated, so we have only 2 times U1 minus U2 minus U4. That's our first equation. Next, again, 2 points are insulated, so it's only twice U2 minus U1 minus U5 equaling 0. For this point as well, we have 2 insulated points, but one is a Dirichlet condition set to 100 degrees Celsius. So it will be 2 times U3 minus U7 equals 100. At U4, there are no insulated points in the 4 neighboring points. Therefore, it will be 4 times U4 minus U1 minus U5 minus U8, and the minus 5 will be brought to the other side to be minus 5. Here it's just 4U5 minus U2 minus U4 minus U6 minus U9. This has one insulated point, so it's minus 3U6 minus U5, U7, and U10. One insulated point, so it's 3U7 minus U3 minus U6 minus U11. 2 insulated points, 2U8 minus U4 minus U9. One insulated point, 3 times U9 minus U5, U8, and U10. No insulated points, so it is simply 4 times U10 minus U6, U9, U11, minus 18, but that gets brought to the other side, being plus 18. And finally, 2 insulated points, so 2U11 minus U7 minus U10 equals 0. All right, those are our 11 linear equations in 11 unknowns. This is the system of linear equations we have to solve, and this will estimate the value of the temperature at each of these interior points. Of course, as we are closer to the fireplace, for example, it should get warmer or closer to 100 degrees Celsius, whereas if we get closer to the window, it should cool down. So here's a system of linear equations. None of the zeros are indicated. And here is the solution to this system of linear equations. All right, so here we have our solution vector, and we will copy those 11 values back to the corresponding points in the room. And we can see that yes, indeed, it is warmest, closest to the fireplace, and as we move away from the fireplace, it cools. At closest to the window, it is the coolest, and you can see that the insulating wall, interior wall, does provide some protection or blockage of the heat. So it's actually quite cool in the vicinity of the window due to that wall blocking the fireplace. All right, so this is one example. We could do the same for the previous example with the PCB, but that would result in a much larger system of linear equations, which we would then solve. So with a little effort, you should realize that we should also be able to create a finite difference approximation of Laplace's equation in 3 dimensions. here would be the formula. As before, the value at each point is the average of the 6 points surrounding it. So again, we can visualize this as follows. If we have the temperature or the voltage or potential at the center point, the voltage or temperature at that point should be the average of the voltages or temperatures at the 6 points surrounding it. Now, some of those points may be other points with unknown voltages. However, some of those could be boundary values. Some of those could be insulated values, in which case we would treat them the same as before. So essentially what we will do is we will find a box in R3 such that the region in which we'd like to approximate the solution to Laplace's equation is entirely contained within that box. And we will define that box as going from a sub x to b sub x within the first coordinate, and so on and so forth for the second and third coordinates. We should choose this region so we can divide it into cubes that have volume h cubed. And so, for example, b sub x minus a sub x is going to be an integer multiple of h. And that integer we will represent by n sub x. Consequently, we will divide all three axes into points x0 through x sub n sub x, y0 through y sub n sub y, and z0 through z sub n sub z. Then we will try to approximate the solution at any interior point. So the approximation of the solution at the point xi, yj, zk will be approximated by an unknown value u sub I, j, and k. As with two dimensions, this is going to define a system of linear equations which we can then solve, and this will give us our solution to Laplace's equation at the interior points. All right, here is one example of such a problem. Suppose we already have a cube such that two opposite faces are either at 100 volts or 100 degrees Celsius. It doesn't matter. And the four remaining sides are at either 0 volts or 0 degrees Celsius. We can choose a value of h so that the number of subintervals we are dividing each dimension into is 30. Now, visualizing the solution can be seen as follows. Here you can see the two sides at 100 and the four sides at 0. And then you can see gradations. So if the temperature is 100 on two of the sides, 0 on four of the sides, you can sort of see dead center. If you were to stand right in the middle, it would be approximately 1/3 of 100, or 33.333 degrees or volts in the center. And then you can also see how as you move towards one of these sides, the temperature either drops or increases depending on which side you're moving towards. You can almost even see a gradient within this image. All right, here's another problem. We have a cube, but now all sides of that cube are kept at 0 volts or 0 degrees Celsius, and there are 3 point sources. Those point sources within the cube are either at 100 volts or 100 degrees Celsius, and we again divide each of the intervals into 30 subintervals. Visualizing this solution, you can see that because there is so much region, all 6 sides that are at 0, as you move away from the 3 point sources, the temperature or voltage drops very, very quickly. And from this image, you can also almost see the gradient. Now, locally around the point sources, it seems as if the temperature drop is almost spherical. However, as you get further and further away, there is some interaction between the 3 point sources. So, for example, that you can see that one region that is bounded by a temperature of only 2 degrees Celsius that surrounds all 3 points. Here's another example of such a problem. Consider a cube. Assume that one of the sides is maintained at 0 volts or at 0 degrees Celsius, and the remaining 5 sides are insulated. Now, assume also that there is a point source in the center of the cube that is either at 100 volts or 100 degrees Celsius. What is the temperature distribution going to be throughout the room? So, for example, how close do you have to be to the center to have a temperature close to 80? What happens if you're standing between the source of heat and the wall that is kept at 0? What happens if the source of heat is between you and the wall that is kept at 0? All right, here is our approximation to the solution if we were to define a system of, well, in this case, we're breaking it up into 14 subintervals. That means 13 points are unknown. Therefore, that would be 13 cubed, but there's a heat source in the center. So that's 13 cubed minus 1 linear equations in 13 cubed minus 1 unknowns. That's a reasonably large system of linear equations on the order of well over 1,000. We could, however, still easily solve this in MATLAB, and it would tell us the temperature at every single point or voltage within the cube. Consequently, we can estimate what the temperature change is going to be throughout the cube in this visualization. So as you can see, if you are standing on the opposite wall away from the wall of cold at the bottom, that the temperature would be a little bit more than 16 degrees Celsius, or the voltage would be just slightly more than 16 volts. Similarly, you can see that if you start at the wall and move away, initially you start having an increase in the temperature or voltage in incremental steps close to the wall, but then as you get further and further away, you get a more significant effect from the temperature or voltage source in the center that is at 100. And of course, as you move towards the voltage or temperature source of 100, it does get warmer, and it almost appears to be a sphere as you approach it. So the temperature increases approximately the same in all directions as you approach the temperature source that is at 100. Okay, let's look at what the equations would be for the above. For most of the points, all of the neighbors are also unknown. And so for most of the points, the linear equation would simply be the expression we see here. However, if one of the 6 neighboring points is the point source that is at 100, then we would replace that one particular value with that value, 100, and that would simplify to the following linear equation, now in 6 unknowns. If one of the 6 neighbors was the wall that is kept at 0, then once again, that one term in the equation would be set to 0, and once again, we have a linear equation in 6 unknowns. Finally, if one of the 6 points is an insulated point, then that term would be removed or set to 0 in the linear equation, as the value at that point would be equal to the point uijk. Consequently, the 2 would cancel each other out and we would be left with 5. Now this is for most of the points. However, there are also points right next to one of the corners or right next to where 2 of the edges meet, where you might have 2 sides that are insulated, or one side that is insulated and one side that is at 0 degrees, or possibly in a corner you could have even more of the sides being either insulated or at 0. So those would also have to be updated. However, as you can imagine, you could probably do this mechanically in a program, but that is definitely beyond the scope of this course. So following this topic, you now understand Laplace's equation and its application to finding steady states to static problems. You know how to convert Laplace's equation into a finite difference equation, and you know how to break a region into a grid of points, be it in 2 or 3 dimensions. You also know how you can convert this grid of points into a system of linear equations which can be solved. Consequently, you've seen 4 examples that included both Dirichlet or fixed boundary values or boundary conditions, and also insulated boundary conditions. Here are the references, acknowledgments, the colophon, and a disclaimer. Cheers!